In 1950, surrounded by massive, glowing electronic cabinets of early British mainframes, mathematician Alan Turing asked a question that sounded almost childish. Can machines think? Ask 10 people what thinking actually means, and you get 10 completely different answers. The word is slippery, rooted in vague assumptions about human biology and the soul, making it nearly impossible to test in any scientific way. Consider trying to judge if a dish at a restaurant is truly authentic. There is no objective measurement. But if you serve it blindly alongside food made by a grandmother from that country, and regular customers cannot tell the difference, the debate over authenticity stops mattering. Turing recognized that debating the philosophy of a mechanical mind was a trap. Instead of trying to define human intelligence, he swapped the mushy question out for a sharper one. He abandoned the argument over consciousness entirely. He decided to invent an entirely new experiment with strict, measurable rules. The foundation of artificial intelligence relies entirely on this pivot. Researchers stopped arguing about what constitutes a thought and built a system to test if a machine could successfully fake one. Turing called his experiment the Imitation Game, though we now know it as the Turing Test. This schematic shows his proposed setup: 3 separate, isolated rooms. One holds a human judge, another a human participant, and the third hides a machine. To prevent physical biases from ruining the data, all communication is restricted to typed text. The judge's job is to figure out who is who by asking questions, while the machine's sole objective is to deceive the judge into believing it is the human. When Turing laid out these rules, he was extremely specific about the hardware. He defined a digital computer using 3 distinct parts: a store for memory, an executive unit to run calculations, and a control to follow instructions. This hardware definition led to his most powerful mathematical breakthrough, the universality property. He argued that if you gave one digital computer enough memory and the right program, it could perfectly imitate any other machine. The phone in your pocket functions as a calculator, a camera, and a music player. It does not have 3 distinct physical mechanisms crammed inside. It is a single universal machine running different software. Turing proved decades ago that giving a robot a humanoid body is completely irrelevant to the actual question of intelligence. The physical form is just a shell. The capability lies entirely in the code. Proposing that metal and wire could rival the human mind was highly controversial in 1950. Knowing this would trigger public anxiety, Turing devoted a large portion of his paper to preemptively dismantling his critics' arguments. Against the claim that only humans have God-given souls, Turing pointed out the arbitrary limit this placed on divine power. If a creator can grant a soul to an animal, nothing theoretically prevents that same creator from doing so for a machine. He also targeted Lady Lovelace's objection, the popular idea that computers can only do exactly what they are programmed to do and never create anything original. Turing dismissed this by observing that machines constantly surprise the people who build them. Still, he admitted that trying to hand code an adult-level, fully formed artificial brain from scratch was a deeply flawed approach. The necessary instructions were simply too vast. His solution was a concept he called the child machine. Instead of building a finished mind, developers should start with a blank slate and allow it to adapt, mutate, and evolve through constant trial and error. To guide this evolution, Turing suggested a system of automated rewards and punishments. The machine would execute a task, receive feedback, and adjust its internal design based on what produced the best outcomes. This exact process of repeated natural selection and reward shaping is the foundational architecture of modern machine learning. It is the precise technique used to train systems like AlphaGo to defeat human champions. This chart plots Turing's historical prediction against the actual timeline of hardware development. He stated that by the year 2000, computers equipped with 1 billion units of storage would achieve a 30% success rate in the imitation game. While the sharp upward curve of storage capacity followed his timeline almost exactly, he drastically underestimated the complexity of the software. Building the physical memory was an engineering hurdle. Writing the code to fill it was vastly harder. Because of that software bottleneck, machines did not start reliably passing informal conversational tests until researchers developed massive large language models in the 2010s and 2020s. But the enduring value of Turing's paper does not hinge on his timeline being perfectly accurate. The lasting legacy of his work was shifting an entire branch of philosophy toward an actionable, testable scientific benchmark. We are currently living inside the experiment he designed. Every time you ask a voice assistant for the weather or read a poem generated by a chatbot, you are communicating with the hidden machine in the other room. Turing never demanded that we scientifically prove a piece of software actually experiences a thought. He simply proposed that if its output is indistinguishable from a human, the debate over its inner life no longer matters.